We probably think of a photon, a little particle of light, as something that just zips from point A to point B in a perfectly straight line. Simple, right? Direct, predictable. But what happens when its path isn't clear? What happens when that photon has to travel through something, like, say, the tissue in your own body? Well, that journey, it turns out, is anything but simple. It's this whole secret life filled with these bizarre and fascinating interactions. The photon can get nudged off course, it can be completely transformed, or it can even just stop existing and give birth to something brand new. So today we're going to pull back that curtain and take a look at this secret life.
So this is the big question, right? This is what we're really digging into. Because the answer isn't just one thing, it's like a whole menu of possibilities. The way a single photon and a single atom interact can play out in wildly different ways. And it all hinges on one single crucial factor. And trust me, understanding this stuff isn't just for physicists. It's the very foundation of things like medical imaging, radiation therapy. Heck, it's how we see the world at all. So let's start the investigation.
All right, so here's how we're going to break it all down. First, we'll set the stage with the absolute basics of how photons and matter even talk to each other. Then, we're going to dive deep into our first case study, this really low-energy thing called the coherent scatter dance. After that, we are going to climb way up the energy ladder to see something that is, frankly, mind-blowing. The moment pure energy becomes actual matter in a process called pair production. And finally, we'll bring it all together and figure out why these two completely different events actually matter in the real world.
Okay, so let's get into it. Imagine a beam of photons, like an X-ray beam, heading into some material. One of three basic things can happen. Some of those photons might just sail right on through without hitting anything. We call that transmission. Others are going to get knocked off their path, kind of like a pinball. That's scattering. And some are just stopped dead in their tracks, their energy totally absorbed by the material. When you add up all the absorption and all the scattering, the overall drop in the beam's power is what we call attenuation. For today, we're going to focus on two very specific interactions at the opposite ends of the energy scale.
Now, if you want to understand which of those things is going to happen, transmission, absorption, or scattering, you have to grasp this one single, most important concept of all. It's all about the energy of that incoming photon. You can think of its energy as the master key. It's what dictates the entire story. A photon with very little energy is going to have a completely different conversation with an atom than a photon that's packed with a ton of energy. That energy level literally sets all the rules for what happens next.
So let's start at the bottom of that ladder, at the low energy end. This is where we find our first interaction. And really, it's less of a violent collision and more like a delicate, synchronized dance. This is what's known as coherent scattering. It's what happens when a photon just doesn't have enough juice to do anything really dramatic, so it engages with the atom in a much, much more subtle way.
You'll hear this process called a few different things, and it's actually pretty useful to know them. You might see it as Rayleigh scattering, or classical scattering, or elastic scattering. They all mean the exact same thing. And the really important word there is elastic. Think about a perfect billiard ball bounce, where one ball hits another and bounces off without losing any speed. That's what's happening here. The photon changes its direction, but it keeps every bit of its original energy. It's just a deflection, not an absorption. So how does this dance actually play out? Well, let's walk through it. First, you've got this low-energy photon cruising along and it approaches an atom. Because its energy is low, its wavelength is long, so it kind of washes over the entire atom at once. This gets us to step 2. The photon's energy field causes all of the atom's electrons to start vibrating or oscillating together in perfect sync. Now this is the cool part. These synchronized vibrating electrons effectively turn into a tiny little antenna. And what do antennas do? They radiate energy. So for step 3, they immediately get rid of that extra energy they just picked up by radiating a brand new photon. And here's the punchline in step 4. Because no energy was actually lost or kept by the atom, this new photon has the exact same energy, the exact same frequency, the exact same wavelength as the original one. The only thing that's different is its direction. It's headed off at a slight angle.
Let's just quickly sum up the key results of this whole thing. First, and this is crucial, no energy is left behind. None. The atom doesn't absorb anything. It all leaves with that new photon. Second, because no energy was lost, the scattered photon is, for all intents and purposes, identical to the one that came in. It's just on a new flight path now. And here's the really critical point for what we'll talk about next. No electron gets knocked out of the atom. There's no photoelectron released. This whole event is just a gentle redirection. And it's most likely to happen with low-energy photons and in materials that have a lot of electrons, like things with high atomic numbers. And this right here is where the rubber meets the road, especially in medicine. Why do we care so much that no photoelectron gets released? Well, in medical imaging, the radiation dose a patient receives isn't really from the initial X-ray photon itself. The real damage dealer is the high-energy electron, the photoelectron, that gets knocked loose by other kinds of interactions. A single one of those ejected electrons can go on a rampage, ionizing thousands of other atoms. But with coherent scattering, that electron is never born. The photon comes in, gets redirected, and leaves. No electron is set loose to cause any biological trouble. And that's why this interaction contributes next to nothing to a patient's radiation dose.
Okay, now let's leave that world of gentle nudges far, far behind. We are about to climb the energy ladder, and I mean way, way up. We're shifting gears from a polite little dance to an act of pure literal creation. We are entering the realm of pair production, an interaction so energetic, so profound, it kind of messes with our whole everyday understanding of how reality works.
Right, so we saw what happens when a photon's energy is low. It causes a little vibration and moves on. But what if it's got an incredible amount of energy? I'm not just talking enough to knock out an electron. I'm talking far, far more than that. When a photon is carrying an absolutely enormous energy payload, it can do something that sounds like it's straight out of science fiction. It can transform its entire being from pure energy into solid matter.
Now, this transformation can't just happen whenever. There is a very specific and very high price of admission. The incoming photon must have an energy of at least 1.02 mega-electron volts. If it has 1.01, nothing happens. It's a hard limit. Below this, pair production is physically impossible. And just to give you some perspective, the X-rays that we use for a chest X-ray are usually somewhere in the range of 30 to 80 kilo-electron volts. This is an energy level more than 10 times higher. We are talking about a seriously high-energy event.
So what is pair production? Okay, here it is. It's an interaction where a photon carrying more than that 1.02 MeV of energy passes super close to the intense electromagnetic field of an atomic nucleus. And in that powerful field, the photon just vanishes. It ceases to exist. And in its place, created from that pure energy, a pair of particles is born. One is a familiar electron, and the other is its antimatter twin, a positron. That's a particle with the exact same mass as an electron, but the opposite charge. This is Einstein's E equals mc squared happening right in front of you in the most direct, stunning way possible. Energy is literally being converted directly into mass.
Let's break down this absolutely incredible event. So, the high-energy photon gets close to a nucleus, it interacts with that powerful field, and poof, it's gone. But why that super-specific 1.02 MeV number? Well, you can think of it like this. If you want to create a particle from pure energy, you have to pay a mass tax. The energy it costs to create one electron from scratch is 0.51 MeV. And to create its antimatter twin, the positron, it also costs 0.51 MeV. So the absolute bare minimum energy you need to create the pair is 0.51 plus 0.51, which equals 1.02 MeV. That's your threshold. Now, if the incoming photon has more energy than that, say 1.5 MeV, the extra is just converted into the kinetic energy, basically the speed of the brand new electron and positron, sending them flying off.
So the key takeaways here are basically the polar opposite of what we saw with coherent scattering. The incoming photon doesn't just change direction, it is completely, utterly gone, absorbed. Its existence is over. And in its place, we have the creation of brand new matter. This whole process is impossible without hitting that strict 1.02 MeV energy minimum, and it leaves you with two new particles that carry on the energy of that original photon.
So we've just taken a journey to two extreme ends of how a photon can behave. One is this quiet, conservative event where nothing really changes. The other is a dramatic, creative act. Now let's put them side by side so we can really lock in the differences and see where they fit in the grand scheme of things.
Looking at them like this makes the contrast just crystal clear. First, the energy level. Low versus ridiculously high. The interaction partner? For coherent scatter, it's the atom's whole cloud of electrons. For pair production, it's the powerful nucleus at the center. The outcome? One is just a simple change in direction. The other is the creation of a matter-antimatter pair. And finally, the energy change. For coherent scatter, there is none. For pair production, it's total 100% absorption. They're just fundamentally different stories, told by photons at completely different points in their lives.
So, where do we actually run into these things? Well, pair production, with that 1.02 MeV requirement, is way outside the energy range of diagnostic radiation. You just don't see it. It's really only important in things like radiation therapy, which uses much higher energies. And what about our gentle little dance, coherent scattering? Well, as you can see here, in the energy range we use for X-rays, it's a really minor player. The vast majority of what happens is dominated by two other processes: the photoelectric effect, where the photon gets totally absorbed, and Compton scatter, where it loses just some of its energy to an electron. So while coherent scattering might add a little bit of noise to an image, its overall impact on the picture and on the patient is tiny compared to the big two.
You know, if you only remember one thing from all of this, let it be this. The secret life of a photon, its entire fate, is dictated by its energy. With low energy, it can just gently nudge an atom and then go on its way totally unchanged. But give that exact same particle of light immense energy, and it can undergo a complete fundamental transformation, turning its very essence from pure energy into actual physical matter.
And that really leads us to a final, much bigger question. We've seen a single thing, a photon, act like a wave that makes electrons dance and then act like a concentrated packet of energy that creates matter out of thin air. This weird dual nature, this ability to have such profoundly different destinies based on just one property, that's the heart and soul of quantum mechanics. It's a reminder that just beneath the surface of the world we see every day, there's another reality that is so much stranger and so much more wonderful than we can possibly imagine. Makes you wonder, what other transformations are just waiting for us to find?